Okay, so we're going to continue. We're going to continue with our discussion on chapter 10, frequency response. Just remind you guys that the two projects, one is due right after the break. So you got to do it. If you don't start, it might be too late. Actually, the project is very simple. Just follow the instructions and get it done. And another project is due on April 20th. So be aware of the deadline. But so what we're going to do is next week, we're going to finish this chapter. And the following week, we're going to talk about feedback. And then within that time, I'm going to talk a little bit about oscillators, because our second project is about oscillators. Yeah, so the second project is also fairly simple, but sometimes a lot of students couldn't get it to work. So you have to probably spend some time. If you build the circuit exactly as it is on the given handout, it should work. But you might have to do a little bit tweaking here and there to make sure you get the oscillation to work. So we'll talk a little bit about that before the break. You guys can do the project during the break, and after the break, one's due right after, and then the other one is actually on April 20th. And think about it, our spring break is actually really late in the semester. So after the spring break, we only have 2 lectures left. That's not much, right? So, I mean, one of them we're going to do it as a review. So you're going to really have 2 lectures left. So time flies very quick, but hopefully you guys are catching up. I know my class is very demanding. It's a quiz every week. You got to study. So if you don't study, you're going to miss something that you cannot do well in the class. So that's the same thing moving on all the way towards the end. 1 week we don't have a quiz, which is after the break. This 1 week we don't have a quiz to give you guys time to work on the project. So that's what we have. But one of the things you guys probably already noticed that what I'm trying to do is really, again, I want to emphasize this, is that just give you sort of understanding of the procedures and the very basic principles that you get the method, how to do this. And when you move on, the book is too thick, too much information. There's no way we can cover it in 1 semester, right? So a lot of information was left out, especially those long derivations of equations. And one equation could take us half of the class time. So we cannot do it. But the idea that what is the principle, like if I want to do it, how can I do it? I mean, just like you guys, everybody today uses calculators, right? Yeah, we can punch numbers on calculator, but the idea is that you cannot understand how to do multiplication and division, right? If you have to do it, you can do it. That's kind of idea we have. When you guys find a job later on, if you do stay in engineering or electrical engineering, you'll find that you always, like, this book is very useful. A lot of people will go back to this book very often, more often than you would think, if you stay in this field, okay? I mean, if you switch to medical or law or economics, that's a different story. But if you want to stay in the field, this book is very useful. But you got to know where to find your information, okay? I mean, if you don't know where to find it, the book has no use. So my idea is that to get you to know where to find it. So, I mean, if you look at the quizzes, you probably understand so far already. If you did your homework, this is basically plugging in the numbers. Okay, although that you really have to understand the small signal circuit to understand the equations, but once you understand that, you will simply plug it in the equations, right? So that's how you get it. So it's not that I want to fail any students. I don't. But you got to study yours, and I do my work, you do yours. So let's work together. That's really the way. So that is being said, today we're going to go through a few things. Apparently next week's quiz is going to be based on what we cover today, right? And then next week, we're going to finish the chapter by talking about low frequency response. In today's lecture and next week's lecture, if I wanted to do it, I would probably spend on the whole time to derive very long equations. So we're not going to do that. So we're going to start like writing the algebra, but we're going to skip all the actual intermediate steps to derive them. And then we get to the actual solution. We say, okay, well, this is how you form this equation to get the actual solution. We neglect the intermediate steps, but then we'll analyze the equation saying, okay, what does it mean to us, right? And then can you draw this frequency response based on the equation? So that's the idea. So it should be fairly simple. By the time you do your quiz, I'm not going to expect you to derive that equation. There's no way you can do that within like 2 hours on your final or even 20 minutes quiz. But you got to understand where the equation comes from, and then say you can apply to that problem. You know how to use it. So that's very important. Okay. So last week we basically we stop at a common source amplifier, and then we were saying, well, we have this final gain. We have two frequencies. We have one frequency which is high frequency, like the 3 dB frequency. What 3 dB means is that at 3 dB, your magnitude drops roughly 3 dB, which is about 30, almost 30%. 70.7 is the number. So 0.707 original value, that's where you got it. And then after that point, your gain is going to drop linearly on a logarithm. This is a logarithm plot. On a linear plot, this is not going to be linear, right? It's going to be like a different. But on a logarithm, it's going to drop linearly, and for every decade of increase, a decade means increase 10 times. For every decade of frequency increase, your gain drops 20 dB. So that's why it's linear. So we call this line minus 20 dB per decade, means dropping 20 dB every decade, every 10 times frequency increase, it drops. So later on next week, we're going to talk about low frequency response. You're going to see that it drops 20 dB for every decrease of frequency. So we're basically going to the other spectrum. Now we are in the high frequency spectrum. So from here, what we did on that was we assumed there was a resistance for the source, for the voltage source. So we signal, and then there's resistance for the signal. This is very common for most of the sources would have some sort of internal resistance. However, sometimes the source resistance is relatively small in comparison to the rest of the circuit. Now, you might say, how small can it be small? Well, you think about it. R pi is typically in the kilo ohms, like 2 to 5 kilo ohms, right? So if your internal resistance is at kilo ohms, it's big because it's comparable. But if your input resistance at the tenth of ohms, let's say it's 500 ohms even, and comparing to 5 kilo ohms, that's relatively small, but not small enough to neglect. But if your resistance is 50 ohms, see, 50 compared to 5K, that's 100 times difference. So that resistance compared is considered really small. We can neglect it basically because it's so small, 100 times smaller, right? So when you neglect it, something happens magically because there's no resistance at the input. Now your voltage source is directly connected to a capacitor. Now, be careful because in circuit theory, you guys were told you cannot connect the voltage source directly onto a capacitor because it's going to create a surge current and things like that. That is true for normal conditions. But here, what we're talking about two things. One is that this is very small. The signals are small. Okay, the capacitors are small. And this is AC. So there's no inrush, right? So it basically considers at the zero cross point, you can try to connect it. So that's one. So you can actually connect a capacitor with the AC input, not a DC. Secondly, what we're saying that it's the resistance small, we neglected. We didn't say it's totally not there. We neglected it for the convenience of our analysis, right? So it's still there, but even if you included it there, after the whole analysis, you'll find that, yeah, that thing does not make much impact, right? So that's why we neglect it. So without that, you see, this circuit becomes fairly simple. In fact, you look at, you have two nodes. There's a G node, there's a D node. And we can write two nodal equations based on this circuit, equivalent circuit. And again, you guys need to know already, well, how to get this small signal circuit, right? So this is small signal circuit, you have CGS, CGD, and you have GM times VGS, RO. The middle part basically is your small signal circuit. So this whole part is your small signal circuit. And we think is external input, RL is your load. And CL, we put it here. The reason we put CL because often CL represent what we call a parasitic capacitance of the output. Normally, this CL is negligible. But for small signal at high frequency, this CL sometimes become significant. We cannot neglect it. Okay. It's parasitic, for example, you have a resistor. That resistor is that big. And which means on the resistor, you have input and output. And between this input and output, there's capacitance. The capacitance is so small that we normally wouldn't bother about it. But in the high frequency response, we have to consider it. Okay, so CL is here. So now you see we can write two equations. Again, so you guys, okay, the first step, understanding the small signal equivalent circuit, right? And then what's internal, what's external. Second step, understanding how to write the nodal equations. So let's write together on node G. So node G has three components. Now, the problem over here is that ISG is a voltage, and the current at SIG on that branch. Can we determine what current? Can we write it? It's a voltage source. There's nothing connected. So therefore, we cannot write current on VSIG. So then what do we know? Well, that nodal equation becomes so simple that VG is equal to VC, right? And that's what you have, okay? And then on the D node, we have 1, 2, 3, 4. We have 5 components, right? So CGD, CGS, RO, RL, CL, and GM times VGS. So what we do is we're going to find like a current. We can write a current all the way to, we can write all the current flowing out so that we can write everything summarized to 0. So we have on the IGD, on the CGD, we will have VO minus VG times S CGD, and then plus GM times VGS plus VO divided by RO plus VO divided by RL, and then plus VO times SCL, and all together it's 0. We write the second equation. So now you know that VG is VSIG, so plug in VG to VSIG, and VG is also same as VGS, right? So also same as VGS. So we replace VGS in this equation, VG and VGS, and now you have VO as a function of VSIG, right? So from here, basically you would simply be able to get VO as a function of VSIG. And that equation, again, we're going to neglect the intermediate step, how to derive it. We find that this VO over VSIG equal to minus GM. The reason I have to write this out, because this is an important equation to understand what does it mean, what it means to us, right? So it has 2 components. The top is 1 over S times CGD divided by GM. And the bottom is 1 plus S times CL plus CGD. Okay. So this equation, if you remember what we had for the previous derivation with SIG, the difference is that we don't have this term. So now we got this term on the numerator. So now let's analyze this circuit. Analyze this equation, see what happens. If we assume S is very, very small, frequency is low, what happens to this equation? So S is very small, is much less than 1, so we can neglect this one. We can neglect this one. So the whole thing becomes 1. And then we have VSIG minus GM times RL prime. See what happened? This is the middle band gain, right? So this common source middle band gain. So which means this only works at the high frequency. Now, if frequency goes really high, what happens? Well, S is very high, and this S is very high. Basically, we can neglect the 1. So that 1 goes away, and we got this one divided by this one, so S cancel. And then minus sign becomes positive, of course. And we have this 2, so we have some sort of volume. So what it says that now, at very low frequency, not really low, but in the middle band, we got the middle band gain. But when the frequency becomes higher, the gain didn't go to 0. Actually, it goes to certain constant. That's interesting, right? Okay, now we have another phenomenon. What happens if the top is like S is has such value that 1 minus this one in the term of amplitude is 0? What happens? You get 0. So which means our gain is going to be somewhere from middle band gain, reduce to 0, and reduce to some other value. Okay, now, of course, we're going to take amplitude. We're not going to look at the minus sign. So we're going to take because this is frequency response, we're going to take the magnitude. So you can imagine in your brain, see what happens. Which means if I draw this, it looks like something like this. So at low frequency, it's a constant. And then it's going to drop. And then at some point, it becomes another constant. Constant, drop, constant. Reason why? Because when S is big enough, this 1 can be neglected, and this S cancel, we get some number. So I'm not going to write the equation because you guys can write it. This middle band gain times this one divided by this one. So that RL actually cancels, and you basically have some sort of, and GM is going to cancel. So the value actually is going to be just CGD over CL plus CGD times, that's it, actually. That's it. So that's your gain. So if you guys have taken 420, if you're not, you're going to take it. You have to take it. E student. If you have not taken, yeah, but if you're taking it, you know that what this is. So this is in the control theory. This is called a 0, and this is called a pole. So you have 1 pole and 1 0, and when the pole and 0, they will cancel at some frequency. So, yeah. Numerator what? Numerator is called a 0. A 0 means when S equal to this value, that's a 0. 0 means when this term is equal to 1, this thing becomes 0. So that's why it's called a 0. It makes the numerator 0 at some point. Okay. Pole is, the bottom is a pole. It's a bottom, so it's a pole. Yeah. So the reason we have this type of curve is because when you guys now can tell me, what is the frequency over here at this point? The 3 dB. Huh? I can hardly understand. On this equation, what frequency this is equivalent to? Yeah, so that's the pole that you have. That's the frequency equivalent to CL plus CGD times RL. 1 over that. That's your pole. And what is the frequency over here then? That's the frequency corresponding to this one, because that's where the 0 comes into play, the pole. So we get 1 0 and then 1 pole. Okay. So this is omega h. We call it, or FH, omega h. And this one we call it F0. So you got 1 0, 1 pole. And the 0, because you see, the 0 is always larger than the pole in high frequency response, because it has to come to this side. So if 0 is before this one,
It could happen, but you will have trouble. Why? Because your gain is going to increase instead of decrease. See what happens is that if just in case I draw it for fun, see what happens if we draw it like this, and it will be like in this. You'll be like, okay, increase and flat. So if you're zero, like if your omega h is here, f0 here, so your frequency is like flat, and then increase, and then flat. But this is going to be troublesome because later on when we talk about chapter 12 or chapter 11, yeah, you're going to know that this is unstable for the system. It's not going to work. So, but we'll cover more of that later on. So this is this is not going to work, right? So this is where we plot the actual curve I plotted last slide. And you can see this is the frequency of your FH. This is your frequency of F0. Oh, actually here, this is F0. And also I forgot to mention that the cross point over here is 0. Yeah, remember that 0 to 0? Yeah, so that's where we have that cross point. And this line drops 20 dB per decade from FH to F0. So yeah, so this is very interesting phenomena, and we're gonna see this in other applications as well. So now we're gonna look at another amplifier. We commonly, we always have two kinds. One is common source, other is common emitter. That's the two most used amplifiers. So for common emitter amplifiers, what you can see here, the overall circuit is almost identical to the MOSFET, right? Except the device is different. Now, if you draw the small signal model, you probably already know also what's going to happen is that we're going to have the small signal model. We're going to draw this one, and you guys already know from the previous lectures, we know that we draw this, right? So this is your RO. I mean, we can connect everything together because they are all ground, right? So V pi. As you look at this circuit, you already know that this circuit is almost identical to the previous circuit, except this R pi. So to analyze this circuit, we'll do the same thing. We'll do a nodal analysis. Like we do a node over here. There's one node over here and one node over here. So a node, like let's call this B and this is C, right? So on node B, we have 4 currents. And we have, if we, again, we have all currents flowing out, you can write the equation to be like V pi minus V Sig divided by R Sig plus V pi over R pi. So this is a term that we don't have in the MOSFET. And then plus V pi times S, what they call this? They call this C pi. S C pi, and plus V pi minus VO, that's the voltage between B and C, times S C mu, and then that's 0. That's the current. And on C we have also 4 currents. So we can write VO minus V pi times S C mu plus GM times V pi plus VO over RO plus VO over RL, 0. Now we write nodal equations based on these two. And now you have 2 equations, and you have 2 variables, which is V pi is a variable, and VO is a variable. By eliminating V pi, you can get the relation between VO and VSIG. So we're going to, again, neglect the actual process. Now you might ask, why, Professor, you always use nodal equations, not loop equations? Well, you could use loop equations, but for circuit like this, nodal is easier because we only have 2 nodes. If you loop, you have 1 loop, 2 loops, 3 loops, 4 loops, 5 loops. Yes, you can write 5 loops, but then your life will become a little bit more difficult, okay? So we can write
And then from here, yeah, so this is the actual circuit that we redraw it here. And again, we have those equations that we wrote on that. We're gonna move on with that. Yeah, this is kind of a little bit simplified analysis, but we're gonna skip that. See, they want to simplify because they can put these two in parallel, right? So, and then they put these two in parallel. And also, they can simplify this one here. Now, I want maybe just go through a little quickly from here. So what happens is, with the voltage source in parallel with the resistance, you actually, that's the circuit over here. You can simplify this into a current source in parallel with the resistance, and then the original resistance here. And then you can convert this back with the resistance and the voltage source, right? So that's why you can do this. Well, this way, you can voltage transfer into current source and put this two in parallel, and then convert this into a voltage source again. So you can do that. So that's why you can have a circuit simplified. Now, this simplification helps a little bit, but I don't think it really helps too much because you still have to write two nodal equations, right? But it just simplifies some of the symbols and make life a little bit easier. So once you derive the actual, let me see. Once you derive the actual relations, let me see if I have the actual equation here. Yeah, I didn't write up, but once you have write the equation, you will find that in fact you have a CEQ, just like the one we did for the MOSFET, and that CEQ is equal to C mu times 1 plus GM RL prime. You see, this equation is exactly identical. And plus C pi, you got the C in. And using C in, you can get your frequency. So your frequency basically is your frequency response. Your FH is eventually going to be 2 pi C in times R sig. Right? Just make sure I write the right thing. Okay, so. Right. So, and of course, this here is a C in, is a prime, is the one that R pi in parallel with R SIG. That's the difference. In a MOSFET, it's just R SIG, but here it's a prime. So you got this FH, and then of course you get the middle band gain. If we write this equation, if we plot this one, if we plot like a F, the gain called AS equal to AM times HS. And if we look at 20 log A, and you get something like this. And then that's your 3 dB, that's your FH. So very almost identical, except the input resistance RSIG becomes SRG prime, which is RSIG in parallel with R pi. So this is the plot that we have. Here, you see, there's a middle band. We have 20 log AM is your middle band gain. Your 3 dB at this frequency, your gain drops 30%. And this line drops 20 dB for every decade. So at this point, you might already know that what happens if RSIG is small. Okay? Same thing. You will get this line go somewhere, it will cross and it will become flat. And that cross point we call T. And I think, for that, when it becomes flat, that point we call the 0. Okay, so we're not gonna spend too much time on that, but so I want to step back one step. So if you look at this circuit over here, it becomes so interesting that initially we had CGD between these two. At the final equation that after all the derivation we had a CEQ. And we plot this one, we found that CEQ actually is just in parallel with C pi. How do we convert from there to here? Like we talked very in detail in the MOSFET, right? So we said, why we could do that.
But you do the same thing for BJT, you'll get this. So it turned out that this person called Miller, I don't know who he is, but this guy might be very smart. So he said, if you have some circuit like this, input and output, and there's a relation between input and output called K. So V2 is K times V1, you already know. And in the middle, there's impedance called Z. Z can be anything, resistance, capacitance, inductance, or combination of them. He said, if you have this circuit, you actually can break down this circuit into two parts. And if you use this equivalent circuit, your life will become so simpler that you basically break down everything into like, just you can analyze each one separate. Does it sound familiar to this? Right? So if we go back again, right? So our circuit was here, C mu is in the middle. That's the Miller circuit. Think about this part is the Miller left, this Miller right, in the middle is C mu. Right? So that's the circuit, and we break down like this. We break it down like this. Okay, and then the question is, how do you do that? How do you do that? Well, because in this equation, we know that V2 is K times V1. So when you do circuit transformation, there's one thing you have to be careful, is the power has to be constant. You cannot change it. If you change the power, the circuit loses its meaning. You have to keep power. So which means if we start to look at I1 will be V1 minus V2 over Z, right? If I want to find V1, I1, how do I find it? The V1 minus K times V1 on the V1 minus V2 divided by Z, I find I, okay? So, and then if I plug in this V2, I get V1 minus K times V1 divided by Z. And if I find I2, like I2, how would you find I2? So on this side, I2, okay. So we find I1, well, I1, okay, sorry. So I1, basically I2 in this circuit is the same. So it's equal to I, okay. So I2 equal to, let me erase this. Okay, so it's I in that circuit. So now we're going to look at, so this circuit equivalent to this circuit over here. And then we're going to look at the circuit on the right hand. On the right hand, we find I1 equal to V1 over Z1. And we find I2 equal to minus V2 over Z2, right? Yes. So now we want to keep the current the same, which means we want to keep I1 equal to I and I2 also equal to I. Okay, so that's what we want to do. We want to keep them the same. So which means we're going to have V1 minus K times V1 divided by Z equal to V1 Z1. So from here, yeah, and then from here we got V2 over Z2 minus equal to V1 minus K V1 divided by Z. And V2 is equal to K times V1, right, divided by Z minus. So by doing this equation here and this equation over minus on here. So by doing these two equations, we can find Z1 and Z2. So what we find is Z1 equal to Z over 1 minus K, and Z2 is Z over 1 minus 1 over K.
So we find Z1 and Z2 from these two equations. Okay, that's actually written over there. So this is very useful in the future, that whenever you see a circuit like a capacitance, for example, in the C mu, you can break this down into two of them. And of course, you have to know the ratio K. So which means you get C1 and C2. For example, in this case, then you have C1 equal to C mu over 1 minus K. And you have C2 equal to C mu over 1 minus 1 over K. 1 over K. Okay, so so if you have C mu in the middle, now you break them down. If you know K, you can simply write this C1 and C2. So now your circuit becomes like two separate circuits. How does it useful? Well, you see, oops, happened. Okay, I don't know. Why it's not moving? I think it's there. Okay. Let me redo it. Yeah. Starting slideshow from print. No. From correct. Okay. So this is useful because, again, if you look at the circuit we have here, instead of having that C mu in the middle, we break that down into C1 and C2. So now you have two nodes, that's right. But you have two separate nodes. Each one is independent. But however, of course, we have to find what a K is in this case. And then that is not that simple. But we'll use this actually in an example. You guys have a homework related to how to calculate. So now we want to move on to talk about the next section is 10.3, I believe, is that we're going to look at the time constants. So the method that we have so far is basically based on two things, basically very simple. One, small signal equivalent circuit. Two, node analysis, nothing else. You guys have circuits, you already learned both, okay? So this is just, we put them together to get the frequency response, high frequency response. But sometimes we find that if the device topology becomes more complex, it becomes more difficult to do the circuit analysis, especially as you introduce so many nodes, so many different components, and it's very difficult to actually derive it. It takes a lot of time. So again, some smart people find that, well, we can actually have a simplified method. Instead, we can do time constants. It's just for high frequency. So what they're saying that for any frequency response, we can write them with AM times HS. So the AM represents your middle band gain, and HS represents your frequency response related to frequency. But frequency is low, HS basically equal to 1, the magnitude, so therefore it's just middle band. But when frequency is higher, it starts to drop. At some point, you get 3 dB frequency, and then you further drop, and so on. But if you have zeros, at some point, it will get again flat, right? So we found that you can write basically this HS. Now, if we take 20 log, it becomes like 20 log AM plus 20 log HS, right? So this is what you have, because this multiplication. So this is basically your constant, and this is your frequency response. And we already know that this frequency response is something like this. Okay, and you get FH, get F0. And this 20 minus 20 dB drop if you have one pole. But sometimes you might have actually more poles. So the generic equation becomes something like this. 1 plus S over omega 0, 1, 1 plus S omega 0, 2. You can have many. And then at the bottom, you can have many poles too. You can have as many as 5, 6, 7 poles and 5, 6, 7 zeros. So each of this is one frequency. But if you look carefully, you'll find that, well, even with all these zeros and poles, actually there's one frequency. There's one frequency that has the most impact on your circuit. And that frequency, we call it a dominant pole. And the dominant pole is actually the lowest frequency, the lowest, second lowest, and highest. So basically means if we write it, this just equal to 1 plus S over omega H1. So that's like omega H is called a dominant pole. So if we draw the circuit, like it's going to look like this. So this one, you start drop, you start flat, drop again, flat, drop again, flat. And each one, each one of this is corresponding to a pole and a 0. So at the 3 dB, you have a pole, and you have 0, it becomes flat. And you have a pole, it drops. And you have flat, and it's 0, and then pole, and then 0. Right? Sometimes you might actually have poles and zeros overlap. Like you have squared, like let's say 1 plus 100th omega squared. And which means you have 2 poles or 2 zeros at the same point. So what that tells you is that if you have 2 poles at this point, so from here to here, how many dB do you think you can get on the drop per decade? It's going to be 40 dB drop. If you have 2 poles at some point, it's going to be 40 dB drop. Okay. So by doing this, what they're saying that we could actually find omega H to be simply the total of omega, sigma, Ri, and Ci. So what it says that if you have I is a integer number, 2, 3, 4. If you have 3 capacitors and 3 resistances, you can find the time constant. RC is a time constant, right? You remember that. So you find out the time constant of each of these R and C together, we add them, we'll get the dominant pole. So to say it is very easy, but to do it actually not that easy. So what do you mean, a time constant? Well, we have to use an actual example to hopefully we have, so we do. So hopefully we have this. So this example is a MOSFET. The MOSFET common source amplifier. We already did one simplification is we had RL prime, which is equal to RL in parallel with RO. So that is already something we simplified. So now we have, if you look at this circuit, we do have 3 capacitors. So CGS, CGD, and CL. Now, if you have your BJT, remember that BJT only changes R pi, and R pi can be in parallel with RSIG and actually simplified to the same circuit eventually. One step, you'll get the same circuit. So what the theorem is saying that we need to find the time constant for each of these capacitors, which means we have to find the time constant for CGS, CGD, and CL. How do you find it? Well, it says that open all cap except the one that you're looking for. So when you find a time constant, let's say for CGS, you would open CGD, you would open RL. Okay. And also, secondly, is short input.
of course, you would open output. I mean, open output means, like in this case, we already have RL, we considered it. So there's nothing else. Nothing else. Like after this we node, there's nothing else. Okay. So that's it doesn't mean we open RL. RL is still there. We're not opening. So based on the two principles, let's start with CGS. So when we look for so when we look for the common constant for CGS, we would short VSIG, we would open CGD, we would open CL. See what do you have the circuit for now if we open it. Basically, we're going to open this, we open this, we short this. So in fact, we got this circuit over here because this is open. So you see what the CGS is connected to. What CGS is connected to is only RSIG. So you have RSIG and you have CGS. And what is time constant of this circuit? Well, let's call tau GS. It's going to be SIG times CGS. Okay, that's that simple. Oh, it's just that. Okay. Okay. Next, we're gonna let me skip this one. Let me go one slide further. Next, we're gonna look at CL. So to do CL, what we need to do? So we short the input, we open this one, we open this one. See what happens now? Well, basically we have this resistor over here, this is ground, and we have this current source, and we have RL prime, and this is ground, this CL. Okay, so the key important here is that how much is the current in here? GM times VGS? Yes, because you look at it. The circuit over here, there's no voltage source, there's no current. So therefore, VGS 0 basically means this is gone. If that is gone, what is the time constant over here? It basically is RL prime times CL. That's that time constant. Wow, that's really simple, right? Okay, well, of course, if we go back one slide, we need to find a CGD. It's not that simple anymore. However, it's simple, but it's not that simple, which means we need to get rid of this, you get rid of this. So now the circuit becomes okay. So this is the circuit we have. This is CGD, RSIG. No, actually, this is short circuit, right? Actually, sorry, this is a short circuit. Remember, the problem is here. So VGS is here. The reason this becomes a little more complicated because this GM times VGS is controlled source, and there's VGS across here, which means it becomes really hard. Like you cannot observe, you cannot find it. So if you cannot find it, what we need to do is we need to look at the equivalent, like Thevenin's equivalent circuit, by finding the total resistance of the circuit. So what we do is instead, in order to find the total resistance, what we're going to do is we're going to replace this thing. We're going to replace this little capacitor with a voltage source, with either current or voltage source. In this book, we put a current source, which means we're going to replace this with current source. So if we replace that with current source, we can find the voltage across here. So if we have Ix and Vx, and the equivalent resistance will be equal to Vx over Ix. So that's how we find it. So we find the equivalent resistance
And then the equivalent circuit of this one will become CGD times R EQ, and then the time constant will equal to CGD times R EQ. So let's call it tau GD. That's what we have. So from here to here, how do you find it? Is we replace that current, the capacitor with the current source. So with the current source, I'm going to find the voltage. So now this of course is now becomes very simple because really there's only one node here, and the current over here is given. So if the current over here is given, how much is VGS? Let's write this together. I mean, this is so simple, we should do it. So VGS. So VGS, you guys write together. How much is VGS? So the current flowing here. So VGS is from there to ground. So this is VGS, right? So from 0 to G, that's VGS, right? And the current is IX. So how much is VGS? Minus RSIG times IX, right? Don't forget the minus sign, so that's important. Okay, so now at node D, we need to write the node equations. So at node D, we have IX going in, and then we have GM times VGS coming out, and then we have VD divided by RL prime. Okay. So now we can plug in VGS over in this equation. And then we should be able to find so when you plug this equation over in this equation, we have VD as a variable. And then we have IX variable, so we can find VD as a function of IX. And then our Vx equal to, VGS minus VD, right? So you from this equation, you can find VD as a function of IX, right? And you plug in here, you got Vx. So now you can find REQ equal to Vx over Ix, and that final equation, let me write down for you. Again, we're gonna skip all the process. Yeah. Let me see. It's quite complicated, but I do have the equation. I have the equation here. It says Vx equal to R SIG in parallel with GM times RL prime plus RL prime times IX. So here you can find REQ is equal to Vx over Ix, right? And then we'll find that tau GD equal to REQ times CGD. So we can plug in that in. So now we can have the total tau equal to tau GS plus tau L plus tau GD. And finally, we got this large equation. Well, we already have VGS. We know it's R SIG times CGS plus tau L is RL times CL, RL prime, and then plus this final term. Final term is going to be RSIG plus, times actually 1 plus GMRL prime plus RL prime times CGD. Now, the reason I want to write this because after you write the three terms together, you find that in this equation here, there's RSIG in this equation as well. So we want to move the terms that are similar, we combine them. once you combine them, we find that this equation equal to is fairly interesting. It becomes CGS plus CGD times 1 plus GM RL prime RSIG plus CGD plus CL L prime. And if you look at what happened with this term, right? This actually is exactly what we got for the FH. So we got really, but then we got this another term related to CL. And so if we neglect the CL, and then this term basically is the same as what we got for the time constants. I mean, for the FH we got from the actual circuit analysis. So this method is useful when you have a complex circuit, you have multiple capacitance and resistances, and you can find the time constant for each of the capacitance just by opening the capacitors, show the input, open the output, and you will get all the constants for each of one of them, and will really simplify your life, okay? So we're going to skip section 10.4, at least for now. If we have time, we'll come back. But if we don't have time, we're probably going to skip it. So it's not going to be on the test next week, right? So let's take a short break, and like 10 minutes, and then we'll come back at what time? 5, yeah. We'll come back at 5, and then we're going to start the very interesting amplifiers, the two other kind of popular amplifiers. let's get started, and then we have a lot to cover. We have a lot to cover in the next couple of stuff, like a section 5 and 6. Again, just like what we have done so far, we're gonna actually skip the actual details, the derivation process. So we're just going to like look at how we draw the circuit and what it means, and eventually we have some kind of results to demonstrate. So for example, we start with the source follower. As we mentioned many times, with amplifiers, this like 2 types. Right? One is the common emitter and a common source, right? So that's amplifier give you a certain gain, but the gain is negative. Remember that emitter band gain is negative. And then we have the source follower and emitter followers. They give you almost unit gain, but they give you very high input resistance, very low output resistance, which is good for like you guys might have heard about buffers, things like that. So in your multi-stage amplifiers, you always have differential input, and you have common source amplifier, and then you have the final stage is always a source follower or emitter follower. So it's important to understand what happens with emitter follower. Well, the emitter follower, apparently we take the output of the emitter. So the idea is that we need to draw the small signal equivalent circuit. Now, to draw the small signal equivalent circuit, apparently we start with the initial model where we don't have the capacitor. Then we add the capacitor. Then we add the external components, right? So we start this one by drawing between the gate, and we're going to just draw it like this, between the gate, the drain, and the source, right? So this is, well, we don't have, this is the model that we don't have the capacitance. This is the MOSFET model. If it's a BJT, we're probably going to skip BJT altogether, because every time we talk, okay, for BJT, what you're doing is you have a RPi. That's all, right? So that's almost the same. And then now the second step is to add the capacitor. So we know that this capacitor over here, this capacitor over here. These are the 2 important capacitors that we cannot ignore. There's some others like CGD and so on. So those ones we're gonna skip those for now. So you have CGD and you have CGS. Those are the 2 most important concepts. Actually, I just remembered that I forgot to mention the Miller effect. Remember that Miller split that we did, split those 2, and we go back saying, well, our previous derivation actually follow exactly what the Miller has said. So that effect of CGD being amplified is called Miller effect. So the capacitance between gate and drain was eventually, remember, we moved that one to be in parallel with CGS, but it's not CGD, it's CGD prime. CGD prime is CGD times 1 plus GM times RL prime. So that's called a Miller effect. That's what this gentleman Miller found it. So it's called Miller effect. But anyway, so right now we have CGD connected between G and D and so on. So this is the circuit now complete with small signal, high frequency small signal model. The next step is we need to connect all the external components. So let's connect the input first. So the input we have RSIG and SIG. And the next we need to connect at the drain. So if you look at the drain, what happened? In this case, small signal for the drain is ground. So that's why we call it a common drain. So the drain is actually the ground. So we ground that. Okay. And then we look at the S. What is connected to S? Well, we have RL and CL. Sometimes this actually is called RS, okay, RSS or whatever, But generally, there's going to be some sort of resistance for a common drain amplifier or source follower. And then the CL is representing the parasitic capacitance of this load side. So we're going to put these two in parallel. and they're both connected to the source of the MOSFET. So which means we're going to have so this is our equivalent circuit, and over this equivalent circuit, apparently there's an opportunity for us to simplify it. We can simplify this circuit before we move forward. Now, so the way to simplify this is to look at the node. Our output is over here. And if you look at what happens with RO, RO is connected from the output to ground. So basically, which means we can move that RO all the way to here, right? So if we move that, it didn't change, which means you move the RO, you will move this RO here, and we move this RO to like here. It doesn't change anything. Basically, it's a ground, right? So and once you move RO over here, you see what happens? The RO and RL in parallel. So it becomes RL prime, right? So now we can actually, so forget the process. We're going to say, we're going to do this one. We're going to do RL prime instead. And then we're going to remove this thing over here because this is removed, right? So now we're going to have this RL prime and CL. So we have this circuit now is simplified, but still, if we want to solve the circuit, we have, we have how many nodes? Basically, we have one node over here. This is one node, and over there, that's a ground, so that's another node. But then we have one node at G, right? So basically, we have two nodes, because that ground we can probably just neglect it. And then we do have two nodes. And with these two nodes, we can write node equations, like over here and over here. Let's write the equation around G. Then around the G node, we have, here is going to be VGS, and this is VO. So this is important. So the node voltage at VG is not VGS. It's VGS plus VO. Now this is ground, okay? And this is VO, and that's VGS is between G and S, right? So that's one critical point. Now sometimes when students start to write node equations, they simply use VGS minus VSIG. That's in the common source, which is correct, but in this case, actually not correct. So we need to have to write VGS plus VO, that's the VG, and minus VSIG divided by RSIG. That gives you the current in this direction from out of gate. And then here we have plus VGS minus VO, which is the voltage across CGS, and then times S, okay, times S. And then plus VGS, VGS plus VO, which is the voltage again at VG, and then times C SCGD equal to 0. So that's the current over in this branch. So we have three currents. One current going this way, one current through CGS, one current through VGD, right? So we have add all three currents, we have 0. We got that node. And at the bottom node, at the source node, it's a little bit actually simpler because we have really 4 currents, and we can have all currents like we can have all currents coming in to actually no, I think I made a mistake somewhere over at the VGS. Yeah, so here I made a mistake here because VGS is the voltage across here, so we don't have to minus VO, so that one has to be removed. So this happens. So you want to write node equation, you should have to be careful to inspect what do you have. So here it should be no, because this is VGS, right? Yeah. So because VGS is the voltage across CGS, so that we don't have to minus VO, right? Okay. For CGD is VGS plus VO to ground, right? So CGD is the voltage from VG, it's VG, right? So VG is VGS plus VO. So that one is correct. But that one we made a mistake. Well, let's correct it, okay? And then now we have S node. Our S node, we have 4 currents. So one current, we can say one current coming in and 2 current coming out. So that make it easier. So current coming in is VGS times SCGS plus GM times VGS, and equal to VO over RL prime plus VO times SCL. So we have 2 currents coming into the node and 2 currents coming out. So now we have these 2 equations derived. So from this equation, apparently, we can derive the VO, the output VO, as a function of VSIG. And again, it's not going to be that simple because we got a couple of things to manipulate. And even if I do it, I would have to do it very carefully. Otherwise, I would make a mistake. But no, the idea is that you can do that. So this is the process. We draw the equation, we draw the small signal model, and we put like all those things here. Like this original model, I started, and then I move RO to the bottom. That's the next slide. Yeah, okay, so actually, yeah, haven't done yet. So now we actually move this RO over to be in parallel with RL. So that's where we got this circuit. Now, the circuit itself included GMB times VBS. We actually neglected here because that current is relatively small. You see here, they actually neglected in this circuit. But instead of drawing the way that I draw, they put it here. So they make it even better to understand the currents. You have one node over here, you have one node over here, which is the same thing, okay? Basically, it's just all the way the same thing. The VGD is to, so you see, this is ground, right? That's why they can move VGD to ground. So we move VGD to ground. However, one thing you have to be careful, CGD and CGS is not in parallel, okay? Because this things connect over here. So that's critically important. And this is another mistake our students often make is that they simply put CGD and CGS in parallel, and they thought they got everything beautifully simply by adding these 2, but that's not correct. So by doing this nodal analysis again, I already did the equation, so we're not going to rewrite it here. But once you get the relation, you'll find that your HS basically is going to be like a complex number. So it's going to be, let me go all the way to what I really actually I have. I want to write this down because this will make it easier to explain. So basically, your HS equal to, or AS, let's call it AS equal to VO over VSIG, which is the gain, equal to AM is the middle band gain, 1 plus S over WZ, 1 plus B1S plus B2 S squared. So basically, you have, in this case, you already know that we have 1, 0, and 2 pole. 1, 0, and 2 pole. Now, I want to actually possibly draw this, but of course, this WZ and B1 and B2 is going to be, we can write it out, which in this case is WZ, I'm going to write WZ over here. So WZ equal to GM over CGS, and AM equal to RL prime times GM over 1 plus RL GM. Well, when RL prime GM is small, if you can neglect it, and then that's where the middle gain becomes, the gain becomes 1. Well, that's why we call it middle follower, because RL prime times GM is relatively small, right? So that you can neglect it. And then actually big, sorry, not small, it's big. So much larger than 1. So that AM equal to 1, that's why I call it emitter follower. And then we have also B1 and B2.
that B1 and B2 is going to be really complex. I'm not going to write it. But what I want you to do is further to break this down into 1 plus S omega Z. And for the bottom, I can do 1 plus S over omega H1 and 1 plus S omega H2. And this you might know that when I break this down into this two, this omega H1, omega H2, it can be a real number, or it can be the same, or it can be a complex. It depending on B1 and B2. So because our solution will be 1 omega H1 is equal to 1. Well, it's what do we call it? Minus B plus the quadratic equation divided by 2a, right? And in this case, a is B2, and b is B1, and c is 1. So, and this number, if b squared minus 4ac equal to 0, you have 2 omega H1 equal to omega H2. But if b squared minus 4ac is larger than 0, you have 2 real poles. 2 real poles. And if b squared minus 4ac is less than 0, you have 2 complex poles. So this is the beauty of this source followers, is that the frequency response is no longer simply just one pole, like saying like that. You actually you could have different scenarios. So all these numbers depending on B1 and B2, which is a very long equation, I could write, but it doesn't make any sense. You guys can find in the book. So when we start to draw the response, and you will find, well, depending on the B1 and B2 value, this curve actually could be very different. So we have drawn here like 1, 2, 3, 4 different curves. And each curve is corresponding to a Q. It's called quotient, and this definition for Q. And we can write that down to actually, I didn't write this down, what Q was. But it really depending on the, so for example, when this one here, the smooth one is where you have 2 like real poles. And this ones, you have like solid 2 real poles. And this has 2 equal poles. And the other one, you have like 2 complex poles. And this line becomes like, going that way. And then you might see this in control theory, and this becomes like some sort of like a resonant. It could go really high, your Q is very high, it's called quotient. And also, another thing you notice that this line, because you have 2 poles, so this line is actually going to be 40 dB instead of 20 dB drop per decade. And you also have a 0, right? So basically, ideally, you will have some sort of curve like this. You have 20 dB, you have 2 real poles, equal real poles, it will drop. And then at some point, at your 0, it's going to become a little bit, because the 0 is going to make it less 20 dB, right? So you have the middle band, 40 dB drop, and then 20 dB drop. So this is where you have this source follower. So yeah, because the equations are very complex, we're really not going to spend the time to derive it. But then, if we look at emitter follower, what I want to do is, again, we want to draw the equivalent circuit, just give you a concept, what happens, right? So for the emitter follower, we draw also the small signal equivalent circuit by drawing this the circuit without the capacitance. Okay, GM. Okay, so this is your B, your C, and your E here. So now we're going to add the two most important capacitors to get the actual small signal model for high frequency. So there's a C mu over here, and there's a C pi over here. Okay, so now we're complete with the small signal model. So again, if you observe the difference, you add R pi instead open circuit for the MOSFET. Right? So now we're going to add our input, and we're going to ground the collector, and then we're going to add this to the load at the emitter, and then this is your output. So similarly, for this one, because R0 is from output to ground, we can bring that RO over here, be in parallel with RL, so you got that one simplified. And the R pi, we can move R pi to be in front of C pi, so the RSIG and C and R pi can be again combined by doing source transformation. So we simplify that one, and then we are going to further because the CGD is connected to ground, we can simplify that. Further simplify that one. So basically, we can yeah. So this is the equivalent circuit original, right? So we're gonna convert this R pi, this one, and we're gonna move this RL to here, and we're gonna move like CGD to ground. CGD, it is the ground, so we're gonna move that to ground. So basically, if I do that, you'll find this circuit becomes RSIG prime, which is, you know that RSIG prime is equal to RSIG in parallel with R pi, right? So, and then here, and we have this C mu to ground. C mu is connected to ground, okay? And then we have C, sorry, without that. We're gonna really look at, so C mu is ground, and C pi is not ground. And then we have this current source. And then we have this one, RL prime and CL. And then here we have a ground. So this is GM and V pi, and this is V pi. So again, the careful thing is that this V pi is, this C mu is not in parallel with this C pi. So C mu is not in parallel with C pi, and C mu is actually connected to ground. And then you have two nodes here, one node here and one node here. So basically write the nodal equations, except this RSIG becomes RSIG prime, everything else is identical. So therefore from here you can really just find out what the, so this is equivalent circuit that we rewrote here. You can now derive the actual expression, which is almost identical, except the input resistance has changed slightly. So that's what we have for the source followers and the emitter followers. Next, because I want to run down to just finish the high frequency response, because really the rest of the analysis follows the same kind of principle. Basically, draw the small signal model, add the capacitance, add the external component, write the nodal equations, derive the relation between input and output, and simplify that into a standard expression. So for high frequency response for differential amplifiers, really the difference is here, if we break this down into two separate circuits, what do you have? I mean, what you have is a common source amplifier. And the common source amplifier, the top is the same.
But the only problem is at bottom, instead of a ground, we now have this resistance, and this one also has this CGD, CGS. It has also its capacitance. Now, ideally, we should probably consider that capacitance as well. But the impact of those capacitance is relatively minor to the actual gain. So in fact, we will neglect it. And then for small signal, there's no current going this way, right? So this has no impact. So basically, if you think about this differential pair, the small signal of the high frequency response is identical to our common source amplifier for the differential mode input. But remember, we also have a common mode input. For common mode input, there's a current flowing here, so this resistance cannot be neglected for common mode, right? So especially when we have the common mode rejection ratio, remember how we got that? Is because even if for common mode, if the input identical on both input, there's nothing current flowing, so we can still neglect it. Only when we when we calculate the common mode rejection ratio, where the common mode input is slightly different because the input is different, but a slight difference between the circuit parameters. Well, we have the circuit, we cannot neglect it. So what we are going to do is for small signal, basically, for example, we take half of the circuit. If we take the half circuit, we have this. And this will be a virtual ground. So this is almost like identical. Now, especially when you have this just simply like, as I said, the differential input and common mode input, so everything is almost identical. Now, we already analyzed this circuit before, common source amplifiers for the gain, so we're not going to repeat it. And if you have this like current source, well, your circuit is not 100% symmetrical, then you would have to consider the current and the resistance of the current source, which over here we split into two RSS. The total is one RSS, one split into two, so two RSS. And then we have this CSS, which is equivalent to the capacitance of the current source. So now you have this circuit. So if you look at this circuit, you might already know, well, this is not a common source, it's not a common drain, because the drain is not grounded and the source is not grounded. But overall, this is equivalent to a common source amplifier with a resistance as the source. We analyzed that before as well. So we have that. So if you look at the common mode gain, if we actually go to derive, like based on this circuit, we can draw the equivalent circuit, and again, we can possibly draw it just here for fun, and you have like very simple circuit to draw, and now you have this. So you have this capacitance here, you have capacitance here, now you have your input right over here, and at the output you also have RL, RO, and you have this ground and this ground. So we have your V in right over here. So basically, this is your equivalent circuit, and we can easily do like again nodal analysis. You have V in, and then you have these two capacitance, and you have one over here. This looks familiar from what we have done before. We have to write the equation and eventually derive the actual derive the actual expressions. Once we do that, you'll find that the common mode gain actually look like this. It's flat, and then it increases. and then at some point it will decrease, which means the common mode gain is going to have a 0 first and then a pole. So this is where we have found that before. Now, you see what happens. Why is this important? Because when you have a common mode input that falls at a certain high frequency range, instead of like having a constant output, it actually gets amplified. That's not good, because the common mode is often something we don't want. It gets amplified. If that gets amplified and your small signal, AC signal, differential signal gets attenuated, that's troublesome, because the common mode rejection ratio becomes smaller, which is not good. You want as big as possible, the common mode rejection ratio. So that's why you have this expression over here. And then once we got to the differential gain, it's the same as the differential gain is exactly the same as a common source amplifier. So it's the same. You have FH, you have this. Okay, everything is the same. The only thing is the common mode. See the common mode gain, it looks like this. Right? So if we overlap this together, we use AD over CM. See what happens? The common mode rejection ratio is AD over ACM, and we do this one, and we take 20 log. Okay, so in the middle band, this two ratio basically is constant. Okay, constant. And then at some point, you have a 0 for the common mode, because RSS and CL or CS. So your gain start to increase for the common mode, but your differential gain is constant. What happens? Your common mode rejection ratio started to decrease. Okay, so that's what happens at FZ. It starts to decrease, and at some point it will decrease more at FH, and then it will be something over crazy at the further. Right? So this is where if your input for your small signal has a common mode input, which basically falls in the middle band, you're good. But if your common mode input actually falls into this region, you might have trouble. If it falls into here, you will have even more trouble, because your common mode rejection ratio becomes so small, which means your output contains the useful information, but also that common mode is something you don't want. So you may not be able even to distinguish, because they become so close, and one may be even bigger than the other one. So that's what we have for the differential amplifiers. And then next, we can take a further look at what happens if you have multi-stage. Well, for this multi-stage, basically you have one stage and a second stage. And you can see these two stages are basically identical. Identical means the input small signal at the first stage gets amplified, and the output gets further amplified. And the gain of each stage is typically in the tens, like 20s, 40s, or 10, 20, 40, whatever, maybe 5. But it's in the number between, I would say, 1 to 100. So the input gets amplified. And if you recall from the previous slide, we had this gain in the middle band, and we have this CMRR start to drop, which is not good. But when you have take the same signal and amplify this output to a second stage, what happens? Which means, well, the middle band is gonna good, but the common mode rejection is getting even worse, right? Because instead of here, you already have like the amplification is here, like here, you already got this and this, right? And then here you got again, now you got another like 2020. So it becomes very, very steep drop in terms of common mode gain.
So this is really bad because your common mode rejection will drop so quickly that any signal following here will be in trouble. So of course, when you design your thing, you want to make sure your signal in the middle band. But of course, your circuit always comes with noise, and you don't know where the noise frequency is going to be. So that's my fault here, and it gets amplified for the common mode, and now you have trouble. So that's why, when we design electronic circuit, there's so much trouble getting in and say, well, I'm using only the middle band. What happened with my signal? Something is not right. And that's because your common mode rejection ratio started to decrease dramatically. So this is, of course, you can analyze this one by, again, drawing the small signal models and adding the capacitors, things like that. We're going to skip that. But remember, we talked many times that we don't like RDs, right? So eventually, these RDs will go away as well. They're going to become current mirror or current source. When you have a current mirror and current source, which means we're going to introduce another transistor that also has its own capacitance, like the CSS, right? We have introduced another one. So this is what happens with our next talk about when you have a current mirror. So what happens is you amplify this pair, but you have those two there. And those two there are going to introduce additional capacitance like CM and CL, right? So, and then we, of course, this is becoming from double-ended input to a single-ended output. Then we could, again, draw the small signal equivalent circuit, adding the capacitors of both transistors and adding that. Now, we actually didn't draw this, right? Because we don't want to analyze everything in one circuit. If we draw the actual common mode resistance over here, the circuit becomes really complex. But this circuit is not for common mode. This is for small, for the differential mode analysis. And we can draw the equivalent circuit. And we are not going to actually spend too much time here because it becomes very complex if we want to derive those equations. But what I wanted to give you is that if you have a current mirror in your circuit, the gain actually becomes interesting. If you derive the actual gain by frequency, you find that you have really a pole and a zero, which is pretty close. And our goal is to calculate this FP2 and FZ, because at FP2, our gain drops 3 dB, but at FZ, our gain goes back to a flat output. And this gain is 1/2 GM. This gain is 1/2. So this zero basically cancels the pole at this point, and the gain becomes 1/2 GM. So this is it really becomes important for the current mirrors. For the current mirror type of load is where your gain becomes so different. Okay. Now you can take 20 log, which gives you the same thing, but the book sometimes misses gain with 20 logarithms, right? So basically, it's a similar thing. So overall, like if you have multi-stage, you would have to add all this high frequency response all together to get the overall high frequency response. So like for differential amplifier, like for the first stage amplifier we had, the first stage is a differential amplifier. And the second stage is a differential, but from double-ended input to single-ended output. Right? And the third stage is a common source source amplifier, and the last stage uses PMOS actually, and the last stage becomes the emitter follower. And so that first stage, each stage has its own frequency response, and their frequency response could be different, and they might actually overlap, but they might not. So overall, that you will have a frequency response is something like I wrote earlier, is going to be something like this. It's going to be 1 plus S over And this becomes 1 plus. You could have, like each stage, you can have 1, 0, 2, 0, or 1 pole to 2 poles, each stage. So you have 4 stages. Basically, you will have at least 4 zeros and 8 poles. So, so if some of the frequencies actually might overlap, but so it becomes like 1 plus S over WP then squared. But sometimes they don't. So if you drop the actual like multi-stage, you look at 20 log A S, and it becomes like this becomes 20 log AN, right? And then it will become something like this. It will drop, it will be flat, it will be drop, it drop more, flat, 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 and drop flat like this. Like each one of them is pole, 0, pole, 0, and maybe another pole, another 0, another pole, another 0. So and if it's like starting with 1 pole, this is called 20 dB. I mean, you have 2 poles at some point, it becomes 40 dB drop. And so here, this one, the very first one, we call dominant pole. So the dominant pole is where you, in your design, you actually needed to consider, because anything above that pole is not good for your signal. So if you know your frequency of your signal, you want to design your pole such that the pole is much higher, at least 10 times higher than your operating frequency, which means if this is say 1 megahertz, and your operating frequency should be 1 kilohertz or below. Otherwise, it's going to get close to here. It's not good. So this is really like we mean by like so far. Okay, you want to well, you get many poles, and we only care this way. But what happens with this range? Even though they don't look like, we don't. Sometimes we say we don't care about it. Because I mean, our frequency is in here. Because we design our dominant pole such that it's 10 times higher than our frequency. So do we care about this region? Normally you wouldn't. But the problem is that when we have a feedback, some of these poles or the zeros are going to start to play. Okay. So it's like, okay, if like, I don't have a good analogy, but when you have a feedback, you have to then be careful. Some of this could come back to haunt you. And your system, okay, so I think a simple example is that, yes, you know your signal is here, and you design your dominant pole is here. But what happens is that in your system, there's a noise coming in, which is at a certain frequency over this region. So normally you wouldn't care because that signal gets attenuated so much, right? And yours gets amplified. But with the feedback, it could possible that this resonance start to happen at this frequency. And instead of that signal gets attenuated, because the feedback make it so strong, that signal gets amplified. And it amplifies so much that it's even more than your actual useful signal. So now you have trouble. Okay, you don't even know which one you get, because the one that you want is not even smaller than the one that you don't want. So that's not really something that would happen. So we will spend a little bit of time on this one, like 2 weeks from now, to go through feedback. I think we have 2 lectures on feedback, and we'll talk about those. But for now, we understand the high frequency response. Then next week, we're going to spend time. So we're going to skip 10.7. Okay, that's like too many equations.
and too much complexity to derive anything. I mean, it would spend 3 hours to derive one circuit, which doesn't make sense. Again, you guys, the important thing is that you guys know the principle, okay, know the idea why, and you know how to draw the small signal model equivalent circuit. That's all you need to know. And then next week, actually, we're going to talk about low frequency response. Is that so far we have talked is really just a high frequency range, like something like this, right? So what happens over this range? When frequency is low, you think you're going to be okay? No, actually, no, because there is a low frequency that's going to also be impacted by the circuit parameters. So we're going to get into those next week. And then I also, because that's not going to take us a whole lecture. It's just I do not plan to derive every single equation. We're going to just again set up the process and write the beginning and the end. Okay. So we're going to also spend some time to go into feedback, and I'm going to spend like maybe 20 minutes also to talk about the oscillators, so that you guys can start do your project during the break. Okay. So that's all for today. We finish early. Any questions? Yeah, I know there's many questions. Yeah, go ahead.
Test next Friday.
Text, yeah, I think next week we have a test, right?
Okay.
Yeah, we have a quiz next Friday. Yes. What section is what? Skip 10.4, and it's on the slides. 10, yeah, 10.8 and 10, I think 10.4 we skip, yeah. Okay, because our quiz is on multiple choices, you're not gonna see you know, a process for you to derive any of these equations. It's gonna be some numerical numbers, it's gonna be some true, false type of answers. And I mean, well, it's all multiple choice, okay? Okay, well, no questions. We'll see you next week. Yeah, sure, go ahead.
Okay, for this one.
Yeah.
Okay, you said it goes down -40 because we have 2 poles.
2 poles, right.
Don't we also have a 0?
Uh,
Or we don't have a 0?
you have a 0.
So
You have
we
a 0.
We have 2 poles. Why is it
You have 2
-40?
poles. And your 0 is probably somewhere over here. Your
So-
0,
So we're just assuming.
which is,
zero far
yeah,
away.
0 far away, yeah. Yeah. Yeah, we do. I think we do. And,
Like a midterm.
no, midterm, it's just regular.
So just like a quiz.
Just quiz, yeah, it's a quiz, yeah.
Okay, a
Yeah,
quiz.
yeah.
Thank you. You
Mm.
said test, I was confused.
No, it's just,
It's just like we had.
yeah, we don't have midterm. It's
Okay.
all quizzes. Yeah.